Section 8.4 Part 2 is our continuation of improper integrals. So, improper integrals with infinite discontinuities. Integrals of functions that become infinite at a point within the interval of integration are also improper integrals. So if f of x is continuous on a to b, but not including a, then the integral from a to b of f of x dx is the limit as some value c approaches a from the right. If f of x is continuous on a to b, but not including b, then the integral from a to b is the limit of the integral from a to c as c approaches b from the left. So if f of x is continuous on a to c union c to b, then from a to b, we can go a to c and c to b. So in other words, at this midpoint between a and b, we have an asymptote. So for example, this function has a vertical asymptote at x equals 1, but I'm trying to integrate from 0 to 2. So I need to break this into two pieces because I can't integrate across the vertical asymptote. So it's continuous from 0 to 1 and 1 to 2. So I can break this into two pieces. I'm now going to take each of these that has a problem at 1 and use a limit. So the first improper integral from 0 to 1 is the limit as c approaches 1 from the left. Remember, if I'm going from 0 to 1 and I want to get close to 1 but not actually get there because of my asymptote, I'm approaching 1 from the left. Keeps messing up, sorry. There we go. And so I'm going to use my improper integral to evaluate this. The antiderivative is 3 times x minus 1 to the 1/3, and then applying the limit as c approaches -1. As c approaches -1, all of this is 0, and I get 3. Working from the other side, our derivative from 1 to 2, we now want to approach 1 from the right. Since I'm going from 1 to 2, I'm approaching 1 from the right. Again, antiderivate and apply your function values, and again we get 3. So the integral from 0 to 2 is the sum of those two integrals, or 6. Let's look at one more. Finding the volume of a solid that is infinite. A solid obtained by revolving the curve y equals x e to the negative x from 0 to infinity. So let's take a look at what this looks like. And on the right-hand side, this curve approaches 0 but never reaches 0. So this is an improper integral due to an infinite side. So again, sorry, this is off the page again. The example of finding the volume of an infinite solid. So the area is pi r squared. So using my function, I find the area. I want to integrate that from 0 to infinity, pull the pi out in front. So now I have this integral from 0 to b as b approaches infinity. Okay, we need to integrate twice. So I've got the first integration by parts, and then the second integration by parts, and then my final integration. If you need practice on integration by parts, go ahead and try this yourself. See if you come up with the right values. So this is my function. You notice how they factored out the e to the negative 2x, found a common denominator to clean it up a little bit. So evaluating this as b approaches infinity from 0 to b. And again, they haven't shown everything here, but we do get pi times 1/4. As all of this approaches infinity, this whole piece approaches 0. Take a look at that closely. If you don't understand why this approaches 0, we need to talk about it in class. Try and fill in some of the missing pieces here for yourself, and we'll talk more about this example if we need to. The remaining slide are your usual chapter tests. I know if you use this. Remember, we've skipped a couple of things in this chapter, so if you run across something that you've never seen, it's probably because we're not doing it. These all look okay. These look okay. We didn't do faster or slower, so you might want to skip those. That should be good. This should be good. And that should be okay as well. So here are your solutions. Use this as you like at the end of the chapter.